Hello student, welcome to your chemistry lab. Today I am discussing reaction mechanism of organic chemistry. I will be discussing substitution reaction, addition reaction and elimination reaction and condensation reaction and also rearrangement reaction in one by one. And today first I will discussing substitution reaction, that is nucleophilic substitution reaction, that is SN2 reaction. Means today I am discussing SN2 reaction. It is very simple and it is very informative and for JEE and NEET, and it is also important in total organic chemistry. So start now. We are watching the whiteboard. Hello student. Reaction mechanism. Organic reaction, it involves the bond breaking and bond forming of covalent bond. Organic reaction are of the following type: substitution reaction, addition reaction, elimination reaction and rearrangement. And first one is substitution reaction. In substitution reaction, one atom or group is substituted by another atom or group. First, nucleophilic substitution reaction. Nucleophilic substitution reaction are two types, one SN1 reaction and one SN2 reaction. First, SN2 reaction. SN2 substitution nucleophilic bimolecular reaction. Given example or given reaction, Rx plus OH negative gives ROH plus X negative, and CH3Br, example CH3Br plus OH gives CH3OH and Br negative. And in this reaction, that is CH3Br plus OH negative gives CH3OH plus Br negative, the rate law for the reaction may be expressed as rate directly proportional to alkyl halide, concentration of alkyl halide and into concentration of nucleophile. That is rate directly proportional to concentration of CH3Br and into concentration of OH negative. And SN2 reaction exhibit second order kinetics, that is reaction is bimolecular and both alkyl halide and the nucleophile appear in rate equation. And next point, the nucleophile attack the carbon holding the leaving group on the rear side, means back side. Its orbital start overlapping with the smaller lobe of sp3 hybrid orbital of carbon atom, whose larger lobe is involved in the formation of bond with the leaving group on opposite side. And mechanism is here OH negative backside attack on CH3Br, and this step is slow and rate determining step, and transition state is formed, and next form inversion product, 100% inversion product. And next, thus a SN2 reaction is a single stage reaction. Departure of leaving group and insertion of nucleophile in its place are simultaneous and not one after other. No intermediate is formed, so SN2 reaction is not accompanied by rearrangement or ring expansion. And next, nucleophile and substrate both are involved in only stage, which is rate determining stage, so it is a bimolecular reaction. If the concentration of any one is increased, collision frequency increases, transition state is formed soon, rate increases. If the concentration of any one decreases, rate decreases. And next point, stereochemistry of the SN2 reaction. From what direction goes the nucleophile approach the substrate in an SN2 reaction? There are two possibilities, front side attack and back side attack. Front side attack, nucleophile approaches from the same side as the leaving group. Back side attack, nucleophile approaches from the side opposite the leaving group. The result of front side and back side attack of nucleophile are illustrated with CH3CHDBr as a substrate and general nucleophile Nu negative. This substrate has the leaving group bonded to a stereogenic center, thus allowing us to see the structural difference that result when nucleophile attack from the two different directions. In front side attack, nucleophile approaches from same side as leaving group forming A. In this example, leaving group was drawn on the right, so nucleophile attack from the right and all other groups remain in their original position because the nucleophile and leaving group are in same position relative to other three groups on carbon. Front side attack result in a retention of configuration around the stereogenic center and reaction and here. So nucleophile attack in front side and we are leaving. So Nu replace we are on the same side. And next, in backside attack, the nucleophile approaches from opposite side or to the leaving group forming B. In this example, the leaving group is drawn on right, so nucleophile attack from the left because nucleophile and leaving group are in opposite position relative to other three groups on carbon, and backside attack result inversion of configuration around the stereogenic center reaction. Here we are see this Nu attack on carbon atom from backside and we are leave us, and from Nu replace we are on opposite side and inversion product are formed. The product of front side and back side attack are different compound. A and B are stereoisomers that are non-superimposable. They are enantiomers, and so this product A with the retention of configuration, that is the from front side attack, and product B only SN2 product with inversion of configuration, that is from backside attack. Two are enantiomer, non-superimposable and optically active. And next, which product is formed in SN2 reaction? When the stereochemistry of the product is determined, only B, the product of backside attack, is formed. One explanation for backside attack is based on electronic argument. Both the nucleophile and leaving group are electron rich and these like charge repel each other. That means nucleophile and electrophile are negatively charged, that is the same charge, that is the like charge. Backside attack keep these two groups as far away from each other as possible. In transition state, nucleophile and leaving group are 180 degree away from each other, but in front side attack two groups are same side and repel each other, and given transition state are showing now. You are see this in backside attack, nucleophile negatively charged, Br negative negatively charged are in 180 degree and far away, no repulsion, that is the opposite side. So transition state of backside are showing, and font side negatively charged Br negative and nucleophile are in same side, repulsion each other. So here energy of activation is high in font side attack, but in back side attack energy of activation is low. So next sample problem. Draw the product including stereochemistry of the following reaction, and given reaction and solution is: in given reaction Br negative is leaving group and Cn negative is the nucleophile. Because SN2 reaction proceed with inversion of configuration and leaving group is drawn above the ring on the wedge, and the nucleophile must come from below ending up to the dash wedge. So product is inversion of configuration at C-Br bond, backside attack convert the cis to trans product, because nucleophile Cn negative attack from below the plane of the ring. So next, the reaction is means SN2 reaction is thermochemically favorable only when stronger base is displaced a weaker base, hence successfully displacement of exothermic. This one step reaction has one transition state and no intermediate step. And given diagram energy and reaction coordinate, here activation energy del H negative and transition state are shown. Here del H negative is negative, del H 0 is negative, so it is exothermic reaction. And next, factors affecting rate of SN2 reaction. First one, nature of substrate. As crowding around the carbon holding the leaving group increases, rear side attack of nucleophile becomes difficult. Means in presence of bulky group, means crowding around the carbon holding leaving group, means presence of bulky group increases, rear side attack of nucleophile becomes difficult, and rate of SN2 reaction goes on decreasing. So primary alkyl halide with 2 hydrogen atom on the carbon holding leaving group is more reactive, as hydrogen are the smallest atom which don't occupy much space, and tertiary alkyl halide is least reactive with 3 alkyl group on the carbon holding leaving group. These are much crowding around it. Nucleophile cannot attack it so easily due to lack of sufficient space. So order is: first methyl chloride, that is the 1 degree, ethyl chloride also 1 degree, and propyl chloride also 1 degree, and next one is 2-chloropropane, that is 2 degree, and third one is 3 degree. So reactivity of SN2 reaction decreases from 1 degree, 2 degree and 3 degree. Means for SN2 reaction 1 degree halide is more favorable, and 2 degree then 2 degree then 3 degree. Means all time SN2 reaction are favorable for 1 degree alkyl halide. So next, presence of pi bond between beta gamma carbon are presence of an atom with lone pair in beta position increase the rate of SN2 reaction due to delocalization of electron cloud in transition state. It increases its stability and transition state is formed more easily, rate increases, and order is: first one is benzyl chloride is more reactive, next allyl chloride, next ethyl chloride. SN2 reactivity decreases. And second example, here SN2 reactivity also decreases. Here CC double bond in alpha position is chlorine, and next is butyl chloride present in CC double bond, pi bond is present, so reactivity increases, and next one don't have any pi bond, so reactivity decreases. And next CH3O CH2Cl is more reactive. CH3O CH2CH2Cl, here alpha and beta position, here chloride in alpha position with respect to OCH3, and next chloride in beta position with respect to OCH3. So SN2 is more reactive, more closer, that is alpha position is more reactive. And next CH3CO CH2Cl is more reactive in presence of pi bond, that is the CO group, and next one no pi bond, so CH3 CH2Cl is less reactive, so SN2 reactivity decreases. And also given order you are see this, and SN2 reactivity decreases. And next, a halogen at bridgehead cannot displaced. Here show this no reaction. Steric effect is responsible for this. Nucleophile cannot approach the carbon holding leaving group. And next, vinyl halide and haloaryl are almost inert to nucleophilic substitution reaction due to the stability acquired by them via resonance. Here resonating structure are showing, but here not complete resonating structure, only one canonical structure are formed showing this. And CX bond acquires partially double bond character, and its displacement requires breaking of strong bond and more energy is necessary. So means why aryl halide or vinyl halide are inert to nucleophilic substitution, because here CX bond is partially double bond character due to resonating structure. So CX bond is stronger and need to more energy to break this bond. So aryl halide and vinyl halide are not perform SN2 or nucleophilic substitution reaction. So next, second one, effect of nucleophile. Nucleophile is a lone pair donor. Nucleophile is which can donate the lone pair easily is a soft nucleophile that which cannot donate it so easily, so it is hard nucleophile. Means nucleophile is a lone pair donor. Nucleophile which can donate the lone pair easily, that is the soft nucleophile. Means soft nucleophiles means which can donate lone pair electron easily is soft, and which can not donate easily, it is a hard nucleophile. The here example gives the ability to donate of lone pair is nucleophilicity. It is also affect the rate of SN2 reaction. Here two nucleophile, one is OH negative and next is C6H5O negative, that is the phenoxide ion, and same compound CH3CH2Cl and CH3CH2Cl attack this form, one is OH and one is C6H5O. Product form CH3CH2OH and next one is CH3CH2O C6H5. In the above example, the first reaction take place more easily because OH negative gives lone pair electron more easily. In second one, its phenoxide ion is more stable due to resonance, and lone pair electron cannot give easily. So first reaction take place more easily. The reason is here OH is better nucleophile than C6H5O negative, which is stabilized by resonance and becomes hard nucleophiles. Means soft nucleophile are more reactive for SN2 reaction, and hard nucleophile is less reactive for SN2 reaction. And next, nucleophilicity depends on several factors. First, if same atom in two pieces donate lone pair, the negatively charged one is better nucleophile than neutral one. That is, CH3O negative is better nucleophile than CH3OH. And second, in period from left to right, nucleophilicity decreases. For example, NH2 negative is better nucleophile than F negative. As the size donor decreases, lone pair is close to its nucleus and more tightly held by it and less readily donated. Above all, electronegativity increases from left to right, so nucleophilicity decreases. Means electronegativity increases, nucleophilicity decreases, so SN2 reaction is rate of SN2 reaction is decreases. Here NH2 negative is more, next OH negative, next F negative. Nucleophilicity decreases, rate of SN2 reaction decreases when they act as a nucleophile in this manner. And next, third point, that is the C. In a group from top to bottom, nucleophilicity increases as the size increases and electronegativity decreases. And first factor is electronegativity. More electronegativity, nucleophilicity is decreases, and less electronegativity, nucleophilicity increases. In a group from top to bottom, nucleophilicity increases as the size increases and electronegativity decreases. That is, I negative is more nucleophile than Br negative than Cl negative. That is the nucleophilicity decrease. Fourth point, D. A species which is stabilized by resonance is not a good nucleophile. Means nucleophile are stabilized by resonance, that is, here no electron or lone pair are donate. So OH negative is less stable and phenoxide ion is more stable because they are resonance stabilization. And next one is carboxylate ion. Here equivalent resonating structure is present, so it is more stable than phenoxide ion. So carboxylate ion have equivalent resonating structure, phenoxide ion also have resonating structure, but OH negative don't have any resonating structure. So resonance stabilized nucleophile is not a good nucleophile. And next, fifth point means E. Solvent also has a profound influence on nucleophilicity. F negative cannot be good nucleophile in polar protic solvent as it surrounded by solvent molecules. So solvated through the hydrogen bond, and it is not in isolated state and cannot attack the carbon holding leaving group easily. So rate of SN2 reaction decreases, and given figure this, here F negative is surrounded by water molecule, that is, water is a polar protic solvent. So in polar protic solvent, good nucleophile are cannot be good nucleophile. So here show this. In DMF, the order is Cl negative, Br negative and I negative. Whereas polar protic solvent, order is I negative, Br negative and Cl negative. So means in presence of solvent, nucleophile, order of nucleophile is changes, and rate of SN2 reaction also changes. So here in polar protic solvent, rate of SN2 reaction decreases. Means in polar protic solvent, in presence of polar protic solvent, SN2 reaction is less reactive, means rate decreases. And next, point F. Size of nucleophile. Due to large size, nucleophile like tertiary butoxide prefer act as a base rather than nucleophile due to steric factor, and given reaction are showing. And so here in presence of tertiary butoxide it form eliminated product, that is alkene, not substituted product rather than ether. So next, nucleophilicity of some atom of group given order are below. S negative, I negative, CH3 C6H5 whole 3 P dot C2H5 whole 2 NH, Cn negative, CH3CO negative, Br negative, C6H5O negative, C6H5 NH2, NH3 pyridine, Cl negative, CH3C double O negative, and F negative, and CH3OH are decreasing order. So next, nucleophiles with withdrawing group are not good nucleophile, means when presence of withdrawing group, nucleophiles are not good nucleophiles. So here it showing that OCH3 and NO2, and OCH3 is soft nucleophile and NO2 is minus I effect, that is the withdrawing group, that is the hard nucleophile. And next, third point, effect of leaving group. Better leaving group is weak base. Leaving group also affect rate of SN2 reaction. Next, both ethyl iodide and ethyl chloride on treatment with aqueous NaOH give ethanol. Ethyl iodide gives the alcohol more easily, as the leaving group in this compound is a weak base and better leaving group. Here example, that is CH3I, CH3CH2I and CH3CH2Cl, ethyl iodide and ethyl chloride react with OH negative, and here ethyl iodide is better and iodide is good leaving group, so showing this reaction. And I negative is a conjugated base of strong acid of HI, and I negative is weak base, becomes better leaving group, so ethyl iodide is more reactive. Cl negative is conjugated base of strong acid HCl, which is comparatively weak acid. Cl negative becomes strong base and poor leaving group. And if the conjugated acid of leaving group is strong acid, that's become better leaving groups. Next, CF3SO3H is a strong acid, so CF3SO3 negative, its conjugated base becomes weak base and better leaving group, means weak base is a better leaving group. Strong acid gives weak conjugated base. So a molecule with CF3SO3 negative is as a leaving group is more reactive towards SN2 reaction. The ability to leave is called nucleophugacity. Nucleophugacity of group ability to leave best in the beginning, and following order are given. N to positive, R, CO, R, and following order are given, showing this. Fourth point, effect of solvent. The rate of SN2 reaction increases when it is carried out in polar aprotic solvent than polar protic solvent. Aprotic solvent don't have any hydrogen connected to oxygen or nitrogen. Acetone CH3COCH3 and dimethyl formamide DMF HCONCH3 whole 3 DMSO dimethyl sulfoxide CH3 whole 2 S double bond O are example of polar aprotic solvent. Water is polar protic, and organic solvent like acetone, DMF, DMSO are polar aprotic solvent. SN2 reaction take place more easily in polar aprotic solvent than polar protic solvent. In protic solvent, the nucleophile develop the attraction with solvent molecules and solvate it. As it is not free state, rate of attack of nucleophile on the substrate decreases. It is explained in before. So next, example of SN2 reaction in which no inversion take place. First point, Anchimeric effect or neighboring group participation, that is NGP. In a molecule, if a nucleophilic group as well as a leaving group both are present, and if a reagent is also added to it, the product ultimately formed may have the same configuration. That is means in presence of NGP group, neighboring participating group are present, no inversion take place in SN2 reaction. Here given example, conversion of 2-chlorobutanoic acid into hydroxy acid is an example. If the R2-chlorobutanoic acid is treated with silver oxide and subsequently with NaOH, the hydroxy butanoic acid form was found to have the same R configuration. COOH, that is carboxylic acid group, R group in the molecule act as a nucleophile and displace the chlorine atom by affecting SN2 reaction by rear side, that is the back side attack on the carbon holding Cl, and 3-centered cyclic ester is formed, and due to intermolecular SN2 reaction and subsequently OH negative attack the lactone and affecting another SN2 reaction, open the ring and product is formed, configuration is written and showing this reaction. Here OH group of carboxylic acid, that is given arrow showing that, is leave the chlorine atom, and OH negative act as a nucleophile, or COOH act as a nucleophile and leave the chlorine group and form a cyclic ring. And next step, OH negative, that is nucleophile, attack on the cyclic ring of this side and form R configuration, that is configuration is written. The configuration is written due to neighboring group participation with 2 SN2 reaction take place successively. And next example, here also same, carboxylic acid leave NH2, first NH2 group react with HNO2 form diazo compound, that is N2 positive, and next O negative, that is of carboxylic acid, that is the OH of carboxylic acid, attacked in backside and leave the N2 and form cyclic ring, and next OH negative attacked on that side and form S configuration, that is configuration is written. So next example 2, the methoxybutane is prepared in 2 different ways. By taking 2 halobutane on treatment with sodium methoxide. In this method, the configuration is inverted as a OCH3 attack and the carbon holding halogen atom in rear side, and reaction are showing, and CH3 O negative, that is OCH3 attack this side and Br is leave and configuration is inverted. So H2-bromobutane to R2-bromobutane are formed. And next, if the secondary butoxide and methyl iodide are taken, no inversion take place and no bond around in asymmetric carbon attack. Here O negative attack to the CH3I and form this, and here configuration is written, that is S configuration to S configuration. So unless the bond around the asymmetric carbon break and no inversion is take place. And next, third, intramolecular nucleophilic substitution, that is SNI. In this reaction also no inversion is take place. Here S configuration of the given compound react with SOCl2. We know that the alcohol react with PCl5, PCl3 and SOCl2 form alkyl halide, and here also we form, but here no change in configuration, that is product of chlorine is also same, so no inversion is take place. And next, in some molecules, due to a change in the priorities of group connecting asymmetric carbon in the product, the configuration is retained in SN2 reaction, that is configuration no inversion take place. So here chlorine is pyrited 1 and CH3, and next is 2, 3, and order is it is S, and same also. So OCH3, which is second priority group in the substrate, becomes first priority group in the product. Configuration is written, and even through 3 there is inversion. And next, I think you are enjoying to watch my video. I think you are understanding the SN2 reaction and also clear all the point. If are not clear, so comment me and I will be replied you. Now I will be coming with in next video with SN1 reaction. So thank you everyone, bye bye.